false negative, or FN. So false negatives means they are not negative, but misclassified as negative. They are actually positive. Positive meaning here C1, right? And misclassified as non-C1, misclassified as non-negative, as negative. Similarly, true negatives, or TN, are the number of instances from non-C1 that misclassified, I'm sorry, but classified correctly as non-C1. And false positives, or FP, or the number of instances from non-C1 but misclassified as C1. An example is here. This example shows the confusion matrix of a model classifying customer churn either yes or no. So there are 152 instances that are from churn equal to yes. So those instances have the target variable churn labeled as yes, and classified also in yes. And 4,220 instances from the class churn equal to no correctly classified as no. There are a number of instances misclassified from yes to no and from no to yes. The total row shows the number of yes, the number of no as predicted, and also the total of yes and the number of no as the actual. From the confusion metric, we can calculate or compute the accuracy or classification rate or recognition rate, which is the percentage of test instances that are correctly classified. So basically you sum all the true positive and the true negative together and divide it by all instances, the number of all the instances. The error rate is 1 minus the accuracy. Or you can do taking the all the number of false positive and false negative divided by the number of all the instances. There is a problem that's called class imbalance problem. One class may be very rare, for example, the number of fraud instances or HIV positive instances. And looking at the sample, you can see the significant majority of the negative class and the minority of the positive class. So this case is problematic. So if your classifier classifies all the instances to the negative class, then if you only look at the accuracy, then accuracy is still very high, and you won't know if or it doesn't reflect that the performance of the classifier actually is very bad. Then you would look at the sensitivity and the specificity. Sensitivity is the true positive rate, which is the number of positives divided by the total number of positive. So true positive divided by the total number of positive. And specificity, also called true negative rate, is defined as number of true negative divided by the number of negative. So with this case, you would have to look at other metrics as well. Precision. Precision is the exactness. Basically, what percentage of instances that the classifier labeled as positive and actually also positive. So it is the number of true positive divided by the sum of true positives and false positive. False positive is number of items that do not belong to a class C but incorrectly classified as belonging to class C. And the precision score of 1 for class C means that every item labeled as C actually indeed belong to C. But be careful here. There is no information about the number of items from C not labeled correctly. And recall basically the completeness. What percentage of positive instances did the classifier labeled as positive? It is the ratio of true positives divided by true positive plus false negative. False negative which actually the positive instances and misclassified as negative, so they are called false negative. And recall 1 means that every item from C was labeled as C, but there is no information about items incorrectly classified as belonging to C. So be careful here. Some other metrics are F measure, also called F1 or F score. It is a harmonic mean of precision and recall. And its metric, recall, and precision are evenly weighted. F beta is a more general matrix. It's also a weighted measure of precision and recall. Assigns beta times as much weight to recall as to precision. Looking at the metric, you can see if we replace beta by 1, then you get exactly F1. So F measure, F1 is actually a special case of F beta. Let's look at an example for classifier evaluation metric. Um, we have true positive, true negative, the total of positive, the total of negative, the total of predicted true, and the total of predicted uh, negative. So it's the predicted of positive and predicted of negatives. So from those we can compute the sensitivity, which is true positive divided by the total number of positive, and you get roughly 98%. And looking at this, we can compute the specificity, which is the number of true negative. This is the true negative divided by the total number of negative, and we get 99%. Also, we can compute the accuracy, which is the number of true positive and true negative divided by the total number of instances. Also, we can compute the precision and recall, which is roughly 88% and 89%. In the case when the number of positive instances is very small and the number of negative instances is very large, and this is the case of imbalance. Then looking at the sensitivity and specificity. Sensitivity is actually low. Also, we can compute precision and recall. Now, for evaluating classifier accuracy, mainly we have Holdout method and cross validation method. In the Holdout method, basically we randomly partition the data set into two independent sets, the training set and the test set. The training set, normally we have 2/3 for training the model, and the rest, which is 1/3, for estimating the accuracy. A variation of this method is a stratified holdout. Stratified holdout samples data such that the distribution in the test and training set are approximately the same as in the initial data. So if in the initial data we have, let's say, 40% for class 1 and 60% for class 2, then we see approximately the same ratio in the trained and the test data set. Another variation is repeated holdout. We repeat holdout for k times and compute the accuracy as the average of all the accuracies. But the problem is that the test sets may overlap. The second method is cross-validation using k folds, and usually k is chosen as 10. We randomly partition the data into k mutually exclusive subsets with approximately equal size. At the ith iteration, use one of the set as the test set and the rest as the training set. One variation of this method is leave one out. Basically, k4 is actually k instances. K here is number of instances. And each time we use one instance for testing and the rest is for training. Also, another variation is stratified cross-validation, similar as we talked about with holdout methods, in which folds are stratified so that class distribution in each fold is approximately the same as that in the initial data. With Bootstrap method, Bootstrap basically works well with small data sets. Basically, we sample the instances uniformly with replacement. The same instance may be selected again to be re-added to the training set. So given a data set with n instances, and if we randomly pick instances from that data set for n times with replacement, that would result in a training set of n samples, n instances, n examples, right? And instances that are not in the training set are used to form the test set. Roughly about 63% of the original data end up in the Bootstrap, and the remaining, which are not in the training set, are used for the test set, and that is about 36%. So this is how we get to that number. If we pick randomly instances, the probability of picking one of them is 1 divided by n, and the probability of not picking is 1 minus 1 divided by n, and that would be repeated for n times. And that's how we get to this number. And we repeat the sampling procedure k times, then the overall accuracy of the model is this. Basically, the average of all the models, of all the all the times for k times, and for each we have a weighted sum for the for the test set and for the chain set. All C curve, all C curve, all C stands for receiver operating characteristics. Basically, it is for visual comparison of classification models. It is originated from signal detection theory. It shows the trade-off between the true positive rate or sensitivity and the false positive rate. Basically, with programming, you would get the true positive rate and the false positive rate and plot true positive rate against false positive rate, and what you get is this. What you get is this. The area under the curve is a measure of accuracy of the model. So the more area you have, the more accuracy the classifier is. The one that is closest to the diagonal line is the less accurate one, and the one actually on the same as the diagonal is the least accurate. So this one is the least. And that one is actually higher. And the one with IUC equal to 0.9 is the highest among those. Leaf chart sorts instances according to their predicted probability of being a true positive. The x-axis is sample size and the y-axis is number of true positives. So in summary, we have metrics for model evaluation, which are accuracy, sensitivity, specificity, precision, recall, F measure, and F beta. Stratified k-fold cost validation is recommended for accuracy estimation. Backend boosting can be used for increasing the overall accuracy by learning and combining a number of individual models. All cycles are useful for selecting a good model, and leaf charts are the measures for measuring classifier performance.